Hi, this is about precipitation and acid-base reactions. That's why I have my hat on today, because when we talk about precipitation, usually that means things are coming out of the sky, maybe rain or snow. However, in chemistry, precipitation is a little bit different. What is a precipitation reaction? Well, it's a double replacement reaction where a solid forms that's separate from the solution. Remember, ionic compounds, when they dissolve, the ions can come apart, and then those separated ions will come together again to form a solid. The precipitate is the name of the solid that forms. Here's a good example of precipitation. Here's a reaction of potassium chromate and barium nitrate. So in letter A, you can see the reactants, and the potassium are the red spheres in this drawing, and the barium are the blue. Nitrates are these little things, and the chromates are those. Now look at what happens over here. You can see that what's forming here is barium chromate, and barium chromate, as you can see, is a yellow color. The other things still floating around in solution are potassium and nitrate ions, and that's what you would see visually here, but the schematic diagram on the left kind of shows you what it would look like if you could look at the thing at the molecular level. There is the net ionic equation for it, the barium ions and the chromate ions forming barium chromate solid. So precipitation reactions produce something sometimes that are solids, of course. That's the idea. So here's some vocabulary that relates to precipitation reactions. Things that are soluble are substances that are not forming the solid. Those are the AQ, or aqueous things in the reaction. Things that form solids are considered insoluble. They cannot dissolve in water, and therefore they are noted by the S in a parenthesis, and that's the solid formation. And some things are slightly soluble, or insoluble part of the time, and these things are just called slightly soluble. Oftentimes things that are insoluble or slightly soluble like this are still noted with the S, because there are certain conditions that could produce the solid, and there might be certain conditions of concentration that would not allow the solid to dissolve. So here's an example of a precipitation reaction, or a question. Which of the following ions form compounds with lead 2 that are generally soluble in water? Now I know you all know this because it was in the packet from the first test, and the answer, of course, is nitrates. Nitrates generally form soluble things, and this is the case with lead nitrate. So you can see that you're really going to have to remember those solubility rules so that you can apply them for these precipitation reactions. One of the questions on the AP exam, question number 4 of the second part, has you write equations, and that's what our goal is, to get you to write those accurately. Alright, so here is a formula equation. We call it a molecular equation. It gives the overall stoichiometry, but not the actual forms of the reactants and products in solution. These reactants and products are shown as compounds. So here is the example of it at the bottom. We're going to use the solubility rules to figure out which ones are solids and which ones are aqueous. So silver nitrate, of course, is aqueous. It has nitrate. Sodium chloride is soluble because sodium is in group 1, and that's aqueous. The two products, silver chloride is actually the solid, and sodium nitrate is the other aqueous product, because again, nitrates are still soluble. I believe my hat from the precipitation is starting to come off, so I'm going to straighten myself up a little bit. Alright, moving on. Alright, now, that's a valuable piece of information, that reaction, but we might want to write what's called a complete ionic equation. These represent the ions, and they show the things that ionize, or can form ions, as ions. So this is the reaction we just had, but notice silver is a +1 charge, and it is aqueous, and nitrate is a -1 charge, and it too is aqueous. So it's shown here broken into its ions. Essentially, you're going to break apart AQ compounds. That's essentially what you do when you write a complete ionic equation. The only thing we don't break apart are solids, liquids, and gases, because they don't form ions. Silver chloride is the solid, and you can notice here, there it is, just listed as a solid. So now we can actually see what's happening in the reaction. But moreover, we really want the net ionic equation. We're not so interested in the complete ionic. And these only contain things that are participating in the reaction. Remember, the spectator ions are removed. So essentially, if we crossed out all the things that were the same in the reactants and the products of the previous slide, we would have this, which says silver ions and chloride ions combine to form silver chloride. So instead of all that other stuff that might be still in solution, we're really not worried about that. We're just simply saying this particular reaction is silver chloride production. Spectator ions are not included, and in this case, that's why the sodium and the nitrate were not included. They were the same on both sides, and they could be canceled. Alright, let's look at the correct formula equation, complete ionic equation, and the net ionic equation for the reaction between cobalt-2 chloride and sodium chloride. Here's the formula. Cobalt chloride, notice it's aqueous, sodium hydroxide aqueous. Cobalt hydroxide is the solid, and sodium chloride is the other aqueous. In the last example, the solid one was produced first as a product. Again, it really doesn't matter the order of the reactants with each other and the products with each other. It just so happens they both put the solid product first. But it doesn't have to be that way. Alright, now, moving ahead, if we want the complete ionic equation, there it is. We're breaking apart this one, it's aqueous, this one that's aqueous, and this one that's aqueous, and you can see their form is down there. What they do too, I will show you, the balanced coefficient they actually put in front of each ion. And that's technically the way to do it. Usually, when I do it, I get lazy and I don't put the coefficients until the end, because essentially what we really want for this is the net ionic equation. It's the net ionic equation that we really care about. It's not so much the complete. And there it is down there. You notice it's pretty easy, if you wanted to, jump from the formula to the net ionic. Now, without going to the complete ionic equation, let me show you how I would do that. I'll erase these markings so you can see what I'm thinking. Alright, so if I looked at the formula equation and I saw cobalt hydroxide as the only solid formed, obviously these ions on the left must stay because they're the things forming the solid. I can see that chlorine is going to be aqueous both times, so I kind of cancel it right here. And this sodium, I'll draw it there to make it look different, also can be canceled. So essentially, if something had been canceled here, like as part of a compound, in this case cobalt chloride, when I rewrite it, I actually write it in its ion form. The same with hydroxide. Where's the what? Ah, look. There is a big typo in this PowerPoint from this company. This should be OH negative AQ, right? The chloride, which I just violently scratched out, as you can see above, was aqueous. And remember, no spectators. Sorry about that. Don't look at those secret answers coming up. Alright, no spectators as part of this. And you can see, before the blackout anyway, how would cobalt and chloride form cobalt hydroxide anyway? Silly slide. So what we're going to be doing is we're going to be taking our stoichiometry that we know about, and we are going to be putting it with these precipitation reactions. Very, very common kinds of questions in the AP exam. So let's try this one. Alright, we have 10 milliliters of a 0.3 molar sodium phosphate solution, and it's reacting with 20 milliliters of a 0.2 molar lead 2 nitrate solution, and assume no volume change. what precipitate will form? So we have to go back to our rules, and I'm going to write the compounds out because we're going to need it. So sodium phosphate is Na3PO4, and the other is lead nitrate. So those are the two reactants. Now, in a double replacement reaction, of course, the two ions that would be on the ends react with each other, and the two on the inside react with each other. So we have NaNO3 as one product, writing compounds correctly, and of course lead, which is a +2, Pb3, and phosphate, which is a -3, would produce lead phosphate. Knowing what I know about solubility rules, of course, all positive, division 1, if you will, column 1 are soluble, so that's AQ. This one's AQ because of nitrate, this is AQ because of nitrate, and this one must be the solid product that's formed. So I'm just going to write the phase of matter, phase notation, if you will, right there. All right, so what's a precipitate? Lead 2 phosphate. And I'm thankful this slide is now correct. What mass of precipitate will form? Well, here we have a situation where we're going to have to do a little bit of math. So that means balancing the equation. So I'm going to do a 2, a 3, and a 6 here. Now, what mass will form, we're going to figure out this way. I'm going to do it up here. How many grams of Pb3PO42 will be produced? Now, because this is a limiting reactant question, we're going to have to do this 2 times to see which one is limiting. Again, if you want to figure out moles, look at the ratio, figure out which was limiting, and then proceed. You can do that. But again, it's pretty easy for me to figure it out. So I'm going to take this piece of information right here. This is the first one. This is about sodium phosphate. Now, 10 milliliters is 0.010 liters. And 0.3 molar is the concentration. If I multiply 0.01 by 30, I actually can get 0.003. And that's the number of moles. Because if you think about molarity is moles per liter, and I multiply by liters, right, then I'm just going to be left with moles. So this is a tricky way to start. So essentially, I have 0.003 moles of this sodium phosphate, and I have 0.004 moles, doing the same thing with the other, of lead nitrate. I might be able to figure out which is limiting, but for me, I probably would just move on. And I'm going to figure out which is limiting. When I do, I will tell you that lead nitrate is limiting, so that the reaction would look like this. Moles of lead nitrate, Pb3, whoops, NO3, 2. And within 1 mole of the product, there are 3 moles of the lead nitrate. Notice the coefficient is a 3. And then the formula mass, which took me a while to calculate, which is 811.54. And when I get done, I get I think I get 1.08, but I'm going to round it to 2 sig figs. So let's see if we're right. Oh, good. We are correct. So that's one thing you can do with it. Now, another kind of question you could have is this. Same situation, so you'll have to remember the balanced equation from before. What is the concentration of nitrate ions left in the solution after the reaction is complete? Well, of course, we produced 1.1 grams of the lead Pb3PO42 of the lead phosphate, and we would like to know how much nitrate ions are left in solution. So how many, and I guess it's going to be molarity, I'm going to do moles. How many moles of nitrate ions are in solution? Now, you will notice that the nitrate ions are spectators. So therefore, the number of moles of nitrate in the beginning is going to be exactly the same as at the end. So all I'm going to do is I'm going to convert from grams to moles using that 811.54 again. And then I'm going to look at the mole ratio, and in this case, between the nitrate and the other one, it is a 1:6 ratio. And when I finish, I get 0.0081 moles of the nitrate ions in 0.03 liters. And that gives us 0.27 molar as the concentration, and indeed that's the answer. But you might say, well, how did you get 30 milliliters? Remember, what you have to do is 10 and 20, and that means when added, 30 milliliters total is the new volume. So you can't just use the 20 milliliters of the original nitrate solution. You actually have to do it, even though it says assume no volume change. I'm not sure why they had to put that there, because that would be a little confusing. I might want to use the 20 if they didn't say don't change the volume. But I think when you mix two solutions, of course, the volume is going to change. So that's how it works with this particular reaction. Moving on to the last kind of question you could be asked, stoichiometrically speaking, about precipitation reactions. Same equation that we had before. This time we're talking about the concentration of phosphate ions. Now this one is a little trickier because phosphate ions actually participate in the formation of the solid. Therefore they're not floating around. So how do we figure out how many moles of phosphate ions there are? Well, we're going to take that 1.1 grams again of the lead phosphate that we could produce. And again, I'm going to go from grams, which is the 811.52, to moles. 1 mole of that compound produces 2 moles of the compound with the phosphate in it, the sodium phosphate. You notice the coefficient of sodium phosphate was a 2. That means 0.0027 moles are needed to make the reaction form a solid. Now, in the beginning, we had 0.003 moles, I believe. So this is begin. So when I subtract these two, so that one gave us that answer. So when I subtract these two, I get 0.0033 moles not needed. In other words, it wasn't needed to form the solid, so it's still floating around in solution. It wasn't all used up. Remember, the sodium phosphate was in excess. So then what we do is we take the number of moles, which in this case is 0.0033, and we divide it by the volume, which is 0.03, which we talked about earlier. And when you work it out, you get 0.011 molar. That's the concentration of the phosphate ions that are not in the solid. Another kind of reaction we'll be looking at in this section very briefly are acid-base. Now I say very briefly because, as you'll notice if you flip through the textbook, there are, I think, 3 chapters that relate to acid-base chemistry that we'll do in a few months. So this is just a little overview of acid-base reactions. And remember, there are different definitions of acids and bases. One is the Bronsted-Lowry definition, and one is the Arrhenius, and there's even the Lewis definition, and definitions beyond that that we don't need to know. But here we're talking about the Bronsted-Lowry definition, which we had in intro. And you can see an acid is a proton donor, a base is a proton acceptor. And for a strong acid and a base, you can see this is the reaction. Water is produced. Titrations, which we will do quite a bit later, is a method for neutralizing an acid with a base or a base with an acid. The equivalence point is when you have had enough acid to neutralize the base perfectly. And you can see on the screen here, these are the professional definitions. The end point is something which we will see later, that when you mix the two substances together, an acid and a base, some indicator tells you when to stop the titration because a color change has occurred. Oftentimes with a strong acid and a base, we would use the indicator phenolphthalein, which turns a bright pink in a base. So let's look at this particular reaction. It says for the titration of sulfuric acid, which is a strong acid, H2SO4, with sodium hydroxide, which is a strong base, NaOH, how many moles of sodium hydroxide would be required to react with 1 liter of 0.5 molar sulfuric acid to reach the end point? In other words, we want to know when the H plus and the OH negative are equal. That's the equivalence point. When those things are equal, then we produce water, and it has neutralized, one has neutralized the other. All right, so for this situation, I think we're going to have to write a reaction. We're going to have to write H2SO4 and NaOH. And again, I'm not worried about phase notation. Na2SO4, at least not yet, and H2O. Okay, a neutralization reaction, of course, an acid and a base produce a salt and water. Sodium sulfate is considered a salt because it contains neither hydrogen or hydroxide. And from that, we're going to have to balance, because the balancing is going to be the important part. Here, I need a 2 here, I need a 2 here. All right, so it tells me I have 1 liter of a 0.5 molar sulfuric acid solution. Well, that's real easy because the volume is in liters, so when I multiply, I get 0.500 moles. It's also 0.500 molar. Now, molarity, you can use the balanced equation to find molarity between things as well as moles. So if we have 0.5 moles of H2SO4, or a molarity of 0.5, we want to know how many moles of this sodium hydroxide I'm going to need. And the answer is 1 mole. It would have a molarity of 1, but we would need 1 mole of it, because you notice if this is 0.5, this is 2 times as much, so this is 1.00. You can certainly set up a dimensional analysis problem if you want to see it out, but that's pretty straightforward.